On December 25, 2023, two of the most powerful space telescopes ever built were pointed at the same patch of Jupiter's north pole at the same time, and they did not see the same thing. The James Webb Space Telescope detected an intense infrared flash, Jupiter's auroral region lighting up in a way that, by any standard model of planetary physics, should have produced a corresponding ultraviolet signature. The Hubble Space Telescope was watching in ultraviolet. It recorded nothing. Same location. Same moment. Two instruments that don't make mistakes in opposite directions. This result was published in Nature Communications in May 2025. The lead researcher, Jonathan Nichols at the University of Leicester, described the emission as something previously thought to be impossible. That paper came out 18 months ago. You probably didn't see a headline about it. That's where this starts. Before getting into what the data shows, it's worth being clear about what we're actually talking about, because Jupiter's aurora is not a scaled-up version of the northern lights. It is a categorically different class of phenomenon. Earth's auroras are driven by solar wind particles following magnetic field lines into the upper atmosphere. The process is relatively well understood. The energy involved is measured in gigawatts on an active night. Jupiter's auroral output runs to roughly 100 terawatts per hemisphere. That's not a rounding difference. That's a different order of magnitude entirely, comparable to the total power output of 100,000 large power stations, sustained continuously on a planet 5 times Earth's diameter. Auroras arrive with energies up to 400 kilo-electron volts, 10 to 30 times the energy of the most intense auroral electrons ever measured at Earth. When the Juno spacecraft entered Jupiter's orbit in July 2016, it carried a specific set of instruments designed to measure this environment directly. JEDI, the Jupiter Energetic Particle Detector instrument built at Johns Hopkins APL, measuring particles from 20 to 500 kilo-electron volts. JD, tracking electron distributions from 0.1 to 100 kilo-electron volts. UVS for ultraviolet imaging. And GIRUM, an infrared mapper. For the first time, a spacecraft was inside the auroral zone rather than observing it from a distance. What it found was not what anyone had modeled. The working assumption going into Juno was that Jupiter's most intense auroras would be driven by the same mechanism that drives Earth's: potential acceleration. A coherent electric field aligned with the magnetic field, pulling electrons downward into the atmosphere along a predictable gradient. Decades of Earth-based auroral research had built and validated this model. There was no strong theoretical reason it shouldn't apply to Jupiter. Barry Mock and his team at Johns Hopkins APL published their analysis of JEDI data in Nature in September 2017. The finding was direct. The brightest auroral events on Jupiter are not driven by potential acceleration. They're driven by a broadband, stochastic process, something more like turbulent wave-particle interaction than the ordered potential structures seen at Earth. The electrons don't arrive in a clean beam. They arrive in a way that suggests the acceleration region itself is chaotic in ways the models hadn't captured. There's a second part to this that's harder to explain away. JEDI was measuring electrons moving both downward into the atmosphere and upward away from it, simultaneously in the same pass. Both populations were anomalously energetic. Both were far more intense than anything comparable at Earth. The energy balance doesn't close cleanly. There's almost certainly a conventional explanation for each individual measurement. But consider the pattern. The most powerful aurora in the solar system is being driven by a mechanism we hadn't predicted, and the particle dynamics above it don't match the models we built to describe it. The paper was published. It was cited. It did not become a story. The 2017 result was unexpected. What came before it was something else, a problem that had been sitting in the literature since the 1970s without a satisfying resolution. Jupiter's upper atmosphere, based on its distance from the Sun and basic radiative transfer calculations, should be cold. The predicted temperature is around -73 degrees Celsius. The measured temperature is approximately plus 426 degrees Celsius. That's a discrepancy of roughly 500 degrees, and it doesn't go away when you refine the models. It had been called the energy crisis of giant planet atmospheres for decades. Part of why this persisted so long is a data problem. The last global temperature map of Jupiter's upper atmosphere before the Keck observations was made in 1993. That map had a spatial resolution of a few pixels across an entire planet. The whole of Jupiter, a body 11 times Earth's diameter, was reduced to 2 or 3 data points. You cannot resolve a localized heating structure at that resolution. You can only confirm that the planet is warmer than it should be, on average, without knowing why. In 2016 and 2017, James O'Donoghue's team used the Keck 2 telescope on Mauna Kea, Hawaii, equipped with the near-infrared spectrograph, to build the first genuinely resolved temperature map of Jupiter's upper atmosphere. What they found, published in Nature in August 2021 with Tom Stallard as a co-author, was a distinct band of intense heating near the auroral boundary, a structure the models had not predicted. The models had assumed that Coriolis forces would trap auroral heating near the poles. The data showed heat propagating toward the equator. Crisis partially resolved. The word partially is doing significant work in that sentence. In September 2022, at the European Planetary Science Congress, O'Donoghue's group presented a further result. They had tracked what they described as a heat wave, a thermal front approximately 130,000 kilometers wide, roughly 10 times Earth's diameter, moving from the auroral region toward the equator at speeds of several thousand kilometers per hour. The leading edge temperature exceeded 700 degrees Celsius. The models had specifically predicted this wouldn't happen. The same Coriolis forces that were supposed to confine auroral heating to the poles should have acted as a barrier. The heat wave crossed that barrier. What's generating the thermal front? What determines its speed? And what ultimately happens to that energy when it reaches the equatorial region? These remain open questions. The observation is confirmed. The mechanism is not. At this point, we have 3 independent anomalies, measured by different instruments over different decades by different research groups. An acceleration mechanism that doesn't match the model, a temperature field that can't be explained by the energy sources we've accounted for, and a large-scale thermal structure that the dynamics model said couldn't propagate as far as it does. Does that seem unusual to you? Because the next one is stranger. Before the December 2023 result, it's worth being precise about the methodology, because the strength of what follows depends entirely on understanding why the measurement is hard to dismiss. H3+, a trihydrogen cation, a molecule formed when hydrogen atoms are ionized in Jupiter's upper atmosphere, is the primary tracer used to map auroral activity in the infrared. Its lifetime in the auroral zone is approximately 150 seconds. This is important. It means H3+ emission is essentially a real-time readout of what's happening in the ionosphere right now, not a smeared record of activity over hours. When you detect a burst of H3+ emission, something is depositing energy in that region within the last 2 to 3 minutes. The reason the simultaneous James Webb Space Telescope and Hubble observation matters is that the 2 instruments are not redundant. They're complementary in a specific way that closes a gap. James Webb Space Telescope's near-infrared camera observes in the near-infrared, tracking H3+ emission. Hubble observes in the ultraviolet, tracking the higher energy electron precipitation that, by every known model of auroral physics, must accompany any significant infrared auroral event. High-energy electrons hit the upper atmosphere, excite hydrogen molecules, produce ultraviolet emission. That's the chain. You cannot get one without the other. If both telescopes are watching the same region and only one detects a signal, you have a problem that isn't instrumental. On December 25, 2023, both telescopes were pointed at Jupiter's northern auroral region as part of a coordinated campaign. Near-infrared camera on James Webb Space Telescope detected H3+ emission events that were, by the team's account, extraordinarily bright, fluctuating on timescales of seconds, which itself was unexpected given the 150-second lifetime of the ion. The signal was not subtle. Hubble's ultraviolet detectors recorded nothing at those coordinates during those events. Nichols and his co-authors spent over a year analyzing the data before publishing in Nature Communications in May 2025. Their conclusion: the infrared emission they observed was generated by a process that does not produce the ultraviolet counterpart that all existing auroral models require it to produce. They described the events as involving low-energy electron precipitation, particles that are energetic enough to light up the infrared, but somehow not energetic enough to leave an ultraviolet trace. The physics of how this is possible within the constraints of what we know about Jupiter's magnetosphere is, in their words, not yet understood. We still don't understand how this happens. Nichols stated in the paper. Not a caveat. Not a suggestion for future work. A direct statement about the current state of the models. 4 anomalies. Measured across 6 decades. Published in peer-reviewed journals. Each one independent. In 2017, the electrons driving Jupiter's brightest auroras are being accelerated by a mechanism that wasn't in the model, and they're doing something with directionality that the energy budget doesn't explain. Since the 1970s, the upper atmosphere is 500 degrees warmer than the models predict, and the heating source has never been fully accounted for. In 2022, a thermal wave 10 Earth diameters wide is propagating across a boundary the dynamics model said it couldn't cross. In 2025, an auroral event produces infrared emission with no ultraviolet counterpart, which by known physics shouldn't be possible. None of these results are classified. None require extraordinary claims to describe. They're in the literature, available to anyone who looks past the summary paragraphs. The European Space Agency JUICE mission is currently in transit to the Jovian system, carrying 7 instruments with Jupiter arrival targeted for 2031. The next generation of coordinated observations is years away. We are, at this moment, in the gap between what the data is showing and what the models can explain. What's worth sitting with is not any single anomaly but their collective shape. 4 independent datasets across different instruments, different decades, different research teams, and in each case, the system behaved in a way the prevailing model said it shouldn't. There's probably a unifying explanation. Almost certainly, there's a physical process operating in Jupiter's magnetosphere and ionosphere that we haven't yet correctly described. Something about how energy moves through that system that our models are missing or misrepresenting. What I don't know, and what the published literature as of May 2025 does not resolve, is what that process is. So here's the question worth leaving with. 4 published anomalies, each independently confirmed, each resisting the same class of models. What does the pattern suggest to you about where the gap in the physics actually is? The data is public. The papers are cited above. Draw your own map.